Hi everyone and welcome to this video on solving constraint optimization problems. In this tutorial, I will talk you through a problem using the KKT method. We will go step by step through the first order conditions and verify the second order conditions, and finally visualize the feasible site and the level curves of the objective function. We are asked to minimize the function, minimize minus x squared minus y squared, subject to the following constraints. 1. X plus y squared is less than or equal to 1. 2. X minus x times y plus 1 is greater than or equal to 0. 3. X plus x times y minus y plus 1 is greater than or equal to 0. To apply the KKT method, we rewrite all constraints in standard form, meaning everything is written as less than or equal to 0. G1 of xy equals x plus y squared minus 1 is less than or equal to 0. G2 is negative x plus xy minus 1 minus 1 is less than or equal to 0. G3 is negative x minus xy minus 1 is less than or equal to 0. So let's talk about step 1, construct the Lagrangian. We now introduce 3 Lagrange multipliers, lambda 1, lambda 2, lambda 3, one for each constraint. We define the Lagrangian as the Lagrangian equals minus x squared minus 1 squared plus lambda 1 times open parenthesis x plus y squared minus 1 close parenthesis plus lambda 2 times open parenthesis negative x plus xy minus y minus 1 close parenthesis plus lambda 3 times open parenthesis negative x minus xy plus y minus 1 close parenthesis. And step 2, KKT first order conditions. We now compute the first order conditions by taking partial derivatives. Partial with respect to x. The partial derivative of L with respect to x is negative 2x plus lambda 1 minus lambda 2 times open parenthesis 1 minus y close parenthesis minus lambda 3 times open parenthesis 1 plus y close parenthesis, and that equals to 0. The partial with respect to y is negative 2y plus 2 lambda 1y plus lambda 2 times open parenthesis x minus 1 close parenthesis plus lambda 3 times open parenthesis 1 minus x close parenthesis equals 0. We must also satisfy primal feasibility. All constraints must be satisfied. G1, G2, and G3 must all be less than or equal to 0. And dual feasibility. All lambda values must be greater than or equal to 0. And finally, complementary slackness. Lambda 1 times x plus y squared minus 1 equals 0. Lambda 2 times negative x plus xy minus y minus 1 equals 0. Lambda 3 times negative x minus xy plus y minus 1 equals 0. So let's talk about step 3, try a feasible point. We test the point x equals 0, y equals 1. Constraint 1 and constraint 3 are bounding at this point. The objective value is minus 1. Step 4, second order conditions. The Hyson is a 2 by 2 mixed tree, negative 2, 0, 0, negative 2. This mixed tree is negative definite, meaning the function is directly concave, since the feasible region is closed, and the point satisfies the KKT conditions. We can form a global minimum. Step 5, graphical support. Let's look at the graph. Red, blue, and green dashed curves are the boundaries of the 3 constraints. The green shaded area shows the feasible region. Circular contours represent level curves of the objective function. The black dot marks the point 0, 1, clearly on the boundary and in feasible site. The lower level curves surround the origin, but only the region inside all 3 constraints is feasible. We can clearly say that the point 0, 1 lies on the boundary and give us the minimum objective value. So let's make a conclusion. We applied the KKT method, verified all first order and second order conditions, and supported our solution graphically. The solution is x stars equals 0, y stars equals 1 with a minimum value of minus 1. That's all. Thanks for watching. Bye.